Hello to everyone, my name is Karime and I'll be sharing with you the content of this project entitled A Novel Green Synthesis for Graphene Using Microwave Hydrothermal Method. This study was a thesis project to obtain my bachelor's degree and it was worked with other partners from Spintronics Corporation. Let's get started. As we know, graphenic materials have gained popularity due to their properties and infinite field of applications it can be part of. Despite this, most of the methods are unaffordable, and for that reason, cheaper methods like Homer and derivatives were developed. However, these methodologies are very toxic due to the reagents used in them. On the other hand, the actual environmental crisis should be considered by science in order to have a green approach. So, this investigation describes a novel, facile, green, and affordable synthesis for graphene and reduced graphene oxide carried out through microwave-assisted hydrothermal method using Opuntia ficus indica extract as providing agent of the intercalating groups and stabilizers. Objectives: use the microwave-assisted hydrothermal synthesis method and adjust it to obtain graphenic materials. Justify the proposed synthesis technique using at least 5 of the 12 principles of green chemistry. And finally, modify the parameters of the Homer's method to transform it into an eco-friendly technique. Okay, before we continue with the experimental part, in a simple way I want you to explain how Homer's method works. In an acid medium, graphite sheets are immersed in order to begin to separate one from the other. Then, when we add an aggressive oxidant, we obtain graphite oxide. Oxygenated groups begin to intercalate themselves into the sheets, increasing interlaminar distance, and as a result, we obtain graphene oxide. The graphene oxide is washed and treated with an ultrasonic bath to eliminate the remaining functional groups and isolate graphene sheets. From this, we can understand the Homer's method requirements. We need a strong acid and an aggressive oxidant. Now, experimental part. Prickly pear extract, the ionized water, and 99% pure natural graphite were added into a flask and taken to the microwave during distinct times of microwave irradiation. First, extract preparation. Clados were washed roughly, then cut into small pieces and incorporated into a flask with water at 80 degrees. As you might know, Opuntia ficus indica has a lot of oxygenated groups such as epoxy, hydroxyl ketones, among others, which will be used as intercalating and stabilizing agents. This meets the first Homer's method requirement, oxidative reagents. Second, the mother solution. Mother solution contains pure graphite, deionized water, and Opuntia ficus indica extract. The pathetic character of water provides an acid medium for the synthesis, which allows the degradation of the oxygenated groups after the intercalation of the same. Third, microwave irradiation. The study was divided into 4 experiments. In this poster, only the first results are shown because of time. Now, microwave radiation allows minimal dissociation of water, so we obtain a hydrogen, ion, and a hydroxyl group. As a consequence, the medium becomes an acid. In addition, supplied energy is enough to degrade the remaining functional groups. Here, steps 2 and 3 fulfill the other Homer's method requirement to have a strong acid. This one-step system permits the oxidation of graphite, the intercalation of the oxygenated groups into the structure, their degradation, and isolation of the sheets to obtain graphene and reduce graphene oxide. Okay, now let's go with the results. The samples were analyzed by different techniques. First, FTIR analysis. In figure 2, the analysis showed the functional groups as carboxyl, hydroxyl, ketones, epoxy, etc. present in all the solutions. Now, in figure 3, we're gonna make a little zoom on the fingerprint of the samples. We can see to the naked eye the high rate of degradation of the functional groups and shifts to left, which means a higher exfoliation rate of the sheets. Figure 4 shows the spectra of XRD analysis, which had to be treated with a deconvolution process to be able to observe all the component bands of the original spectra. The first peak fit, centered at 21.7 degrees, is attributed to the graphene. The second peak fit denotes the obtaining of reduced graphene oxide in the solutions, since the characteristic peak is exhibited at 26.28 degrees. As we can see, there are peaks marked with an asterisk belonging to calcium oxalate, a common compound in the prickly pear cactus. As XRD analysis, the ultraviolet visible spectra has a deconvolution treatment to observe the phases in the solution and their percentages. Figure 5 shows the deconvoluted graph of ultraviolet visible analysis for experiment number 4. The first plant present in the rate at 258 nanometers is attributed to the presence of a graphene. The second peak at 274 nanometers to RGO. and a third band is visible at 330 nanometers about, belonging to the extract. Discussion and conclusions. Characterization data prove the presence of graphene and RGO, and it also provides valuable information about the material. From FTIR analysis was observable a high degradation rate of the functional groups, and the shift to the left let us understand that the material is highly exfoliated. XRD analysis indicates the presence of the two phases in the solution. Also, the convolution data showed values of 4.09 angstroms for the interlaminar distance of the graphene sheets. Furthermore, a crystallite size of 1.9 nanometers obtained with shared equation. Moreover, from this last value, the exfoliation yield is obtained, which equals to 3 sheets about. Data from ultraviolet visible analysis corroborate the presence of two phases. Also, the peaks left shifts indicate a low-dimensional material. In turn, the analysis data allows to obtain the yield of the materials in the solution, 60% for graphene and 30% for RGO. And in comparison with traditional methods with yields of 98%, these values for a completely green synthesis route result highly favorable. The newly presented method results in a facile, affordable, effective, and overall scalable route to synthesize graphene and reduce graphene oxide, supported in green chemistry, fulfilling 9 of the 12 principles and based on the microwave-assisted hydrothermal method for the homers and derivatives method replacement.